So in the last lecture, I introduced the idea of how to discuss the concept of quantum chaos. And it has to be handled a little bit with care because the usual classical definition that small perturbations diverge doesn't go through directly. The reason for that being that quantum states are density matrices in a symplectic space. Symplectic structure is the same as what is known in classical physics as a phase space, but it comes with a condition that whatever you defined as an elemental area, it remains conserved. During evolution, and this this is a fundamental property of quantum theory, that the elemental area is essentially the size of Planck's constant. It always comes with a pair of conjugate variables. Most common instances are position and momenta, and you multiply the dimension of position and momentum, you get angular momentum, which is the dimension of the Planck's constant. So that is the story, but the difference with classical physics is this element is non-zero, and the area remains conserved. So the whatever you want to call it, instability in the evolution can only occur through distortion of this area. And I gave a simple example which is not really chaos, but good enough to illustrate the instability, and that was the situation for an ordinary oscillator with quadratic functions, and there is a simple version which can be described in two ways. One of them is the so-called inverted oscillator, and the other is the regular harmonic oscillator. The only thing which is different is the potential proportional to x square changes sign. And I showed that the evolution matrix for inverted oscillator has evolution eigenvalues are actually the exponent. parameterize at e raised to lambda times t. In this case, is plus or minus 1, and the other case is plus or minus I. This we know very well. If you put a e raised to I, well, in units of omega frequency, this is just the sinusoidal behavior of a harmonic oscillator evolution. But if you invert it, the eigenvalues change to plus minus 1. One of the direction will grow, the other direction will contract. So this was a illustrative example, but not real chaos. And from the point of view of understanding chaos, there is a much more popular model which is used in lots of studies, both classical as well as quantum, and today I will describe that. Goes under the name of a kicked top. As the name suggests, it's basically is an object which is spinning, and it undergoes some type of kicks or jerks in its evolution, and the combination of rotation and these jerks gives non-trivial dynamics. So the Hamiltonian, in some normalization, I will write down as a term proportional to jz square, where z is the axis of rotation, and there is a direction for giving the kick, and those things are instantaneous, separated by time interval of t. So, not t, tau. So, there are two terms. One can try to visualize what these two terms contribute. This term proportional to jz square is just a direct analog of what happens in a harmonic oscillator. Instead of a momentum, you have angular momentum. But what does it do to the angle? So, well, you can go and understand what happens to position and momenta. So, if the term is p square, that gives rise to a force, and if a position is positive, it will increase. If it is negative, it will decrease. So, here the same thing applies to the angle, that if the angle is positive, it will increase. If the angle is negative, it will decrease. And if you imagine now that what happens with that in the rotation, it is actually a twist. Okay. The positive, it goes in one direction. If it is negative, it goes in the opposite direction. So, this creates a twist in the rotational dynamics. And this is some which is linear in the momentum, angular momentum. So, all it will do, if this was only the term without anything else, is a familiar thing which happens to an object in a fixed field. It is just gives a uniform rotation. But here it is a rotation, but it occurs in some normalization at a specific times. So, you twist it, then you rotate, and twist it, rotate, And the non-triviality comes from the fact that the direction of a twist and the direction of rotations are different. Twist is around, say, z-axis, rotation is about y-axis. So this is a and the model has a non-trivial behavior when both these terms are present simultaneously. Okay. If one of them is absent, then you can solve the whole thing regularly, just a regular behavior of a certain type, and there is nothing non-trivial in it. But when both of them are simultaneously present, which are in some sense dependent on this coupling constant, one of them I have written as kappa, the other is p. The j here is just an absolute normalization for the angular momentum, because there are two powers here. There is a one power to make it the same dimension as proportional to j, and tau is just a duration of the interval between the kicks. So that is the model, and what is known? Well, first classical version. So okay. Or yeah, let me first just integrate this thing out because it's not too complicated. So because this thing occurs instantaneously, so there is a uniform evolution by this and some instantaneous transformers like this. I can write the operator which is exponential of this in the quantum theory as a product of two factors which kind of alternate. So this is the evolution over a finite interval tau, which takes basically one step, and this is the instantaneous action at the end of the step, and this is the evolution which occurs before that. Nothing is too complicated inside it, but this is a so-called periodic process. The same operator will keep on occurring at every interval of tau, and there is a name for it which is called Floquet evolution. Floquet is the name of a scientist who studied this thing extensively. So there is a time dependence, but it's periodic in time with step size equal to tau. And there are various things one can adjust for the sake of normalization. So this time provides some scale, which is part of the, well, evolution process, and you can fix it in some units, whatever you want. And equivalently, people either fix tau as some value or one of these normalization constant as some value, etc. And doesn't matter too much. Okay. So let me now write down the classical behavior coming from integrating this equation is well known. I will just give you the answer that some convention is chosen. I think one of the common choices is make this rotation by pi by 2. So it goes from, say, the initial state is along z axis. After rotation, it will lie in the xy plane. Just a pi by 2 rotation, which is the best value for studying the effect of the kick. If the kick is small or less, the disturbance from z axis is smaller. So this is what people studied, and then for small kappa, behavior is, or rather evolution, and there is a critical value kappa equal to 4. The evolution becomes chaotic. Yeah.
What is periodic? The u tau periodic or
Time evolution is periodic.
time evolution? It means testing is also undone. It will be untwisted after a period tau.
No, the evolution operator is periodic in time. I'm not talking about the state. I'm talking about the evolution. This first step will be u tau, another next step will be another u tau, third step will be another u tau. That is what I mean by periodic.
That's in RHS, no tau is present. In the formula of u tau, no tau is present.
Yes.
No time is present.
Yeah. This doesn't have time. Time is only here.
That is constant. Time is not in RHS. Does that mean it is constant? Not dependent on time. For a period of tau time.
The operator doesn't depend on time, but it acts periodically in time.
Okay.
Just take any periodic description you have studied, Fourier series, oscillations, whatever it is. The operator is periodic in time. What happens to the state will obtain by putting the operator as an action on the state.
So just to clarify, the conjugate variables in this case are the angular momentum and the
Angle.
angle. So the angle defines the state of the state.
Yeah, but you have to look at it in a broader sense, that it's not only one variable which you can focus on, you have to always focus on the conjugate pair if you want to understand chaos. Hmm? There are various ways of defining it. I will um, come to that, but I had mentioned in the previous uh, class that you can take a unit sphere, which is the space for the density matrix, and it has two variables, theta and phi, and conjugate pair is actually cosine theta and phi. The measure of integration factorizes is cos theta cross product with phi, d cos theta, d phi. So now let me describe the angular version, and for that this model actually offers a nice description which allows you to understand the role played by this quantization of the area. Okay. So that follows from the angular momentum algebra, well known in quantum mechanics. So fixed value of j, there are two j plus 1 states going from jz equal to minus j2 plus. Okay. All these states are perfectly equivalent when the angular momentum is actually a symmetry of the problem. What you choose as z and how you label it, it's a matter of choice of a basis, but there are so many equivalent states. And the quantum algebra is defined by the commutation rule, which is given by the algebra commutator of ji and j is I times epsilon ijk times jk. Epsilon ijk is antisymmetric symbol. So now I can rewrite this thing slightly differently to bring in the concept of elemental area, that I'm going to normalize the components of the angular momentum by the overall value j. Okay. Because this j is a variable, it can have arbitrary value. I will just write it down. And there will be one more factor of 1 over g. The components are all normalized, so they will have values, say, between plus and minus 1, because these things go from plus j to minus j, they normalize. But what this does is you can do something non-trivial. That I take a large j limit, commutator disappears, and you have classical behavior. Because everything in quantum theory is because of commutators, If they go away, you have classical physics. So here now is a way to effectively adjust the Planck constant. Planck constant I didn't write down explicitly anywhere, but basically J behaves like inverse Planck constant. And I can tune it between different values and see what happens to classical versus quantum behavior.
By tuning the J, we are changing the Planck constant or internal.
I'm changing the magnitude of the commutator. That's all that matters. Here, if I had taken commutator of x and p, it was I 2 pi I h, and there was no way for me to change it. Here is the equivalent commutator, but I can change the value. And so you can study the dynamics as a function of this quantization condition without worrying about what you call what is the numerical magnitude of this extracted from some experiment, etc., etc. All that is kind of bypassed. And it turns out that this limit is rather straightforward and it is smooth. So this is related to what I had mentioned last time in the coherent state description. That coherent states provided a smooth way to go from the quantum behavior to classical behavior, and this description allows you to construct what are called spin coherent states, where instead of what you call changing the energy of the state, which is what you do with coherent state, you just change the value of J. Okay. So they are conveniently defined, and for every value of J, you can define the states. So for a specific value of J, there will be 2J plus 1 states. Okay. So they have this elemental area is 4 pi divided by 2J plus 1. 4 pi is the surface area of the Bloch sphere. There is no other space that you need. Magnitude is fixed, but how many you put in inside, that depends on the value of J, and then all of them are equivalent. And by changing J, this is how you are tuning the elemental area. Okay.
The small k is the revolution, k equal to 4 changes to k.
Yeah, so one can now study the dynamics of this Hamiltonian by the usual rules, whatever you can construct. In classical theory, you just have to write the Hamilton's equation of motion and find what happens to a point on the Bloch sphere after every one iteration, and it goes all over the place. Sometimes it will go in little circles like a harmonic oscillator, and sometimes it will jump around, and that is what is studied in terms of when it is regular and when it is kind of chaotic.
That means in the chaotic evolution, we cannot predict the state. Right? I mean, even after, like, suppose we are applying multiple u of terms,
Yeah.
some particular number of terms, we get a state mathematically. But that that state does not represent the actual state because the system has not been.
Yeah, so in the classical theory, it will be defined exactly by this rule. You take 2 points which are only slightly different from each other, apply a certain number of iteration and see where they are going to land up. And if they remain close to enough each other, that is well behaved, no problem. But if they start diverging, it is considered a signature of chaos. And that appears for this, you have to put some values for p and kappa. P is equal to pi by 2, that is where kappa equal to 4, the trajectories become diverging. So how do you define this explicitly? And there is a trick. And you take the so-called maximum weight state where Jz is equal to J. It's always it is unique for any value of J. You can always find what that particular state is. You can write down its explicit form if you want. I will come across that soon enough. And the convenience comes from the fact that this has a unique decomposition, and that is it's a tensor product of 2j qubits. There is only one way to reach here from qubits, and that is you have to take the maximum weight, completely factorized. So this it allows you to do very many calculations nicely, and that is the reason for making this particular choice. And then general state which I will denote by this label omega to denote angular coordinates is defined as rotation operator of omega acting on this state j, where this is the usual polar coordinate description. Yeah.
Clarify the notation, like what's the significance of the repeated labels?
Hmm?
What is meant by maximum weight?
This is a standard notation for this is angular momentum and the third component. That is how the states are defined. So I'm setting Jz equal to J, and because it has a unique decomposition.
Tensor product of those qubits. This is the coherent state.
Hmm?
Tensor product of those qubits. Is it the coherent state?
This is the definition of the coherent state. Take this state, maximum wave state, and rotate it by the angular operator whatever generates the rotation, and it gives nice property which I can write down. Uh, so uh, the usual definitions of rotation about some fixed axis is the exponent should have j dotted with n. N is the axis. Okay, so this is I jx cos jx as a okay. Theta is angle of rotation, so I have to put those things in. And these are the two components which survive. Jx sin phi and jy cos phi. The reason the third one doesn't appear is, well, convention of defining a constant, but Jz is a eigenoperator for this, and it just produces a phase, which doesn't matter. But the defining property now for this state is that if I calculate what is the expectation value of the angular momentum operator, all the three components in this particular system, and that will produce what you expect from the decomposition into Cartesian coordinates. Yeah. It's not 0, it's equal to j. Yeah. Not in quantum mechanics. What are the eigenvalues of j square in quantum algebra? It is j times j plus 1. Classical thing, it is jx square plus jy plus jz square, but not in quantum theory. That is precisely all connected with this non-commutating variables. There is something extra.
Why we have taken 2j number of qubits? Why we have taken 2j number of qubits? Tensor products are among 2j qubits.
You have to add up to this number. No, there is half here.
Yes.
How many stops of half are needed to go to j?
Yes, 2j.
Basically, these are just the polar coordinates on the Bloch sphere. And the purpose of, well, there is a convention put inside here, but the characteristic properties of the coherent state is reflected by this particular identity. So what is the expectation value of the angular momentum operator? It is given by the 3 Cartesian coordinates. Okay. If you want, you can take this, do some jugglery, calculate all the eigenvalues, and you will end up with this particular result.
Is this like a signature of its classical behavior?
Hmm?
Is this expression?
This is to say that this states omega is a close approximation to the classical behavior, and that is why it's labeled as a coherent state. Okay, if you take large J, then it will literally become the classical state. These commutators will basically go to 0. But for finite J, there will be something coming from the commutators and sitting inside all those things. And well, is another way of writing it, which is also quite obvious, which is what is the total J operator? It is what is the symbol I should use? Okay. This is a set of 2J qubits, and the 2J qubits will have total angular momentum operator, which is just the sum of the individual qubits, and each qubit contributes half of the Pauli matrix. That's the normalization which we use for defining angular momentum of a qubit. And if you plug in all those things, there is a nice expression which comes out from this definition, and that is something which is used all the time in defining a qubit. Yeah, the coherent state omega is nothing but what you define for a qubit raised to power 2j. And 0 and 1 are the usual eigenstate of a qubit. And this is how qubits are parameterized on a block sphere. So, the point of all this thing is to generate a nice description of the spin states which can connect classical behavior on one side and quantum behavior on the other side by just increasing the number of qubits. Nothing more complicated than that. And yeah, many of those things are, well, are kind of unusual at the first sight, but it's nothing but rewriting the angular momentum algebra in a particular convention, and you can work it out. This has been around for a century or whatever it is. It's a long history, and well, if you want to understand it, you can work it through once, but nothing complicated in it. So there is yet another convention connected with this notation, which is useful, and that is a so-called tangent plane, or what is also called a stereographic projection, which literally means that uh, we take a block sphere and draw tangent plane to it at the North Pole, and use now a very simple geometric construction. So the opposite thing will be 1, that any point on the sphere given by this coordinates, you map onto the plane to get map from the spherical surface to a plane. And this is a 1:1 map, and the 0 remains at 0, but as you vary this, you will find that 1 will get mapped to infinity. And this is actually a plane, so the whole thing is symmetric about rotation with this axis phi. So the angle phi doesn't change in this mapping, but theta gets mapped to the radial coordinate. And this is a very useful construction to know for, again, what happens to these particular states, and the map can be worked out very easily. So this is theta, and so this is theta over 2, and then you do some jugglery, whatever it is. So this plane coordinates are the radial part is written commonly as tan theta by 2. Well, you take this unit, if you take the diameter equal to 1, this distance is tan theta by 2. You can put a proportionality constant in front if you want, but that doesn't make any difference. It cancels out in the normalizations. And so you can take all these states and transform it to this new coordinate if you want. Or to keep on changing. Phi doesn't change, theta keeps on changing in a particular way. And the nice thing which comes out is this property that if I try to find out what is the overlap between this state, which I had defined on a sphere, and this new coordinate parameterization, what it is, and so it turns out to be just a simple power of z, one particular degree. And this is a tower of 2j plus 1 states built on the lowest states which has j equal to minus z, jz. In this case, the first degree will be just 1. And then every new state, this number will go up by 1 unit up to 2j plus 1 units. The same sequence, but it turns out to be a very simple representation. There is a normalization constant in front, which is some function of all these values of j and jz, but that is not important. The important thing is it's just a simple monomial. And in describing now the dynamics of the spin coherent state, this turns out to be a very useful property. That you can do all operations, whatever it is, just on a single power of z and see what happens. There are well, I can write down the identities also. It can work it out. The expressions for x, y, and z angular momentum components. In the polar coordinates, you may have seen it many number of times in the mathematical physics textbooks, some d by d theta and d by d phi and all those kind of things in some particular way. Here the simplest one happens to be the value of jz, which is just given by this very simple structure. Z times d by dz just produces what is there in the power. And then you remove j. So that is iron. And these other two things can be worked out with little effort. So let me not make any sign mistakes. Z squared is a little complicated, but and this may look little complicated, but the easier way to remember this computation is not look at jx and jy individually, but look at the raising and lowering operators, which are jx plus ijy and jx minus ijy. And with the simple description, all it's going to do is raise the power by 1 unit or reduce it by 1 unit. So if I take say jx plus ijy, or I think one of them will just give this part will combine in nice way. This I is there, but it will go away on the other side, and I think which one is easier? Jx minus ijy is easier. So then these two terms will cancel out, and this will add, the half will go away with that, and then it will be just d by dz, which will bring this exponent down by 1 unit. There are different things which are going to appear in the normalization, but that is understood with some convention. But the main thing is what is the power of z. It will increase by 1 unit or it will decrease by 1 unit. And these are the two operators which basically do that particular job. So So this is again something which is worth learning about in addition to the block sphere convention, which is standard. It's a useful algebra for several kind of calculations. And then the analog of this evolution equation is given by the standard rule of quantum mechanics. How is this going to change? Well, evaluate the commutator with h. And with all these rules, it can be worked out. Well, h is a whole bunch of operators, which is it's written over here. So you have to now calculate the commutators of jz and jy with z, which is soluble in all these kind of things. I will write down the answer only because it's kind of instructive for all I need. Minus what is the convention I was using? And this brings out a nice feature which emphasizes what is this elemental area going to do to the dynamics. So there are two terms. One of them is proportional to z. The other one has this kick, which is proportional to z square plus 1. And you can look at it individually. The first term is dz by dt given by I times z. So you can solve for it exactly. It is just going to give a sinusoidal function e raised to I z t. This is just a uniform rotation in this stereographic coordinate. So this kappa gives uniform and what does the other stuff do? If I ignore this, um, then it is going to be some instantaneous change, but instantaneous change in what? So you can well do the integral of this thing also exactly. This is a dz by dt proportional to z square by z square plus 1 will give you hyperbolic tangent function. It's connected to the fact that you use some tangent mapping over there as well. So this gives a change in phase. And why phase? Because there is a quadratic function over here. So the phase on one side is not going to be the same as the phase in another side. And actually, yeah, it more phase changes, but can actually put it together with a radius also. Or you can better to call it a radial jump, which involves both change in radius as well as a phase, with the jump step is let me call it some delta, and the expression is delta times tan inverse z is equal to minus p by 2. So that this radial jump is the magnitude of this. It depends on the location in some complicated way, depend on the coordinate z itself. And together with this, so one of them is going round and round, the other one is going in and out, and they will produce some complicated story. But if only one term is there, then the evolution becomes completely regular. So because you can work out the exact integrals, there is nothing more. So the point of it is that both these terms must be present to give some non-trivial dynamics, which will relate to what you are looking for in chaos. That is fine. But now look at the structure of the two terms. One thing which has appeared kind of automatically is this factor of 2j minus 1. So the condition for non-trivial evolution in addition to the parameters which were there in the Hamiltonian, needs this stuff also to be non-zero. And what is this particular factor? J equal to half the single qubit. There is no chaotic behavior for a single qubit. You go back to the original definition, it would have been obvious because I wrote down a quadratic term. And if I just single qubit, it will be sigma z. Sigma z square is identity, that doesn't do anything. It will just have this one evolution which is well understood. You will keep on giving a kick. But this whole analysis actually gives a little bit understanding of what happens that you try writing down the most general Hamiltonian for a single qubit. It is just sigma dot b. There is no nonlinear term you can write down for the evolution of a single qubit. This is something which I mentioned earlier in a different construct. And if you don't have a nonlinear function, there is not going to be any chaos whatsoever. So now one can ask, what is this connection to these various things which I wrote down with varying j and some elemental area, that if I take j equal to half, there are only two states which you can associate in some sense, say the northern hemisphere and the southern hemisphere, nothing more than that, just two parts of the Bloch sphere. And these two areas are so large that the fluctuations which are generated by some dynamics of nonlinearity, they get wiped out. So it goes back to the classical definition that what you wanted was the evolution trajectories of two nearby points to diverge. What quantum theory did was that these are not 2 points, these are 2 elemental areas. And so whatever the trajectories you are talking about have to be smeared over this particular area. If the smearing is very large, it is just going to wipe out the fluctuation. And this is what happens explicitly for j equal to half. You cannot generate chaos for it. So This is a, yeah, in some sense, this quantum smearing suppresses chaos.
Means there will be no fluctuations in this case.
Hmm?
There will be no fluctuations in this case.
Yeah, under this evolution, there will be only rotation.
This rotation is being provided by the magnetic field, direction of the magnetic.
Whatever external parameter you put in, I had put some kappa, p, whatever it is, some constant.
There was some discrete times rotation kicks. Here also at discrete times are continuous.
You can put whatever time constant you want to put in, it doesn't matter. You can multiply it by delta functions in time, some periodic. All kind of things can be absorbed in whatever you mean by the magnetic field. But it is something external to the system. That's all that matters. It's not part of the degrees of freedom of the system.
If elemental area is large, so how can we interpret it as a no fluctuation? The fluctuation inside the area, what can we say?
Large or small is qualitative. What appeared explicitly here is j equal to half, in which case this thing disappears. And you can now study, and people have done that numerically, that put the next value, j equal to 1. Does this behavior appear? And the answer is yes, it does appear. And j equal to 1 is the smallest value where you can see some dynamics of this fluctuation. So, well, the study of chaos is basically the small disturbance in the initial state, what will happen to it as a function of time. And that small disturbance in the initial state I am calling fluctuation. And this is just something to keep in the background of understanding a different topic. But now I can address the point of what connection does it have with the quantum algorithms and the computation, etc., which we want to study. And here is something which is kind of used as a black box. So the point I had mentioned last time, that in dealing with variational algorithms, you want to generate a variety of initial states as a function of some parameters and then tune the parameters in some way. So the question is, what are good states? And I had mentioned earlier that you don't want to change your circuit too much, you want to change only the parameters. And this analysis tells you that something which can generate a variety of parameters, maybe sometimes regular, maybe sometimes irregular, uh, you can use it efficiently in a fixed circuit. And that is in the sense that this chaotic dynamics uh, can be included in the variational algorithms. And here now uh, I can give the common you want to generate this complicated state, you generate it by 1 qubit and 2 qubit operations because they are sufficient to cover the Hilbert space. And this is something which I had discussed in some detail last time. And now I can say that I can choose a specific sequence of this 1 qubit and 2 qubit operations to generate a set of variational wave function. Uh, and the choice is what is known as random field Ising. And you will find this in all kind of papers without any explanation of why they use such a system, but it's you can write it in actually not this, make it more general. And you'll just find this circuit drawn in the papers. There are some single qubit rotations which are buried inside here, and this is a 2 qubit coupling. So this is something like the CZ gate, and this is a 1 qubit rotation. And people use it because it sort of works. But the point which I want to make is that there is a connection between this structure and this chaotic Hamiltonian which I wrote down. It's essentially the same thing. And this the other expression is nothing but a mean field limit of this Hamiltonian. Mean field means that you consider the interaction, but it is common everywhere. Just written in a background of some average field over all the remainders, and this beta I in general is dependent on I, but well, if you make it a constant, it will become a term like this pjy over there, and if you make the other term constant, it is nothing but jz square. And so if that kind of averaged out Hamiltonian is versatile enough, this is more versatile than the scheme, and it is capable of generating many different kind of maps. Okay. So the purpose is so that you wanted a good circuit which has a possibility to generate all kind of variational parameters. You keep the circuit fixed, and for different problems you will have different choices of the parameters. Sometimes it will be regular, sometimes it will be irregular, but it can cover all of them.
Different parameters means we can change the alphas and betas to get different thetas.
Yeah. There, many choices of this thing is actually done dynamically in many of these algorithms. You calculate the expectation value of h and then you minimize it. And that direction in which you decrease the expectation value will give you the values of alpha and beta, whatever they are.
So you can cover the whole inverted space.
Hmm? Yeah, I mean, the fact is that you already know that 1 qubit and 2 qubit can cover the whole Hilbert space, but you want to simplify it as much as possible and still cover the variety which you require. Okay. So this evolution basically gives you whatever you want, and then the implementation is like this, just a Floquet evolution. Okay, so then so what you do in the variational calculation is you write down that operator for the single cycle and just apply it iteratively many times. and you decide how many iterations you need before you get a good estimate of the whatever the minimum value of the Hamiltonian. And you play around with this to some extent. And the point is that this repetitive or the periodic evolution makes life easy. You keep a fixed circuit, you just tune by saying that I will apply it 5 times, 10 times, whatever it is, before I get the good approximation for the wave function. So that is done in many of these variational algorithms to figure out well, good set of parameters.
So this Floquet evolution is essentially periodically driven system in time, right?
Yeah.
So when we are considering this Heisenberg's big change, how is it that under mean-field approximation such a shift sharply isolation?
Under a mean field, it becomes that that system is also that is actually periodic by construction, but what people use is they take this thing but use it again by a periodic construction. It's not necessary that it should be used with a periodic system, but periodic version is easier to implement and it is good enough to do the job. That is the point. So you write various circuits, and in the papers you will see it that there will be a box of gates, and you just repeat that box so many number of times before you reach a final result.
Is the Trotter step of this Hamiltonian equivalent to that?
You can call it trotter in that version, etc., but literally it is identical steps, so it is much more appropriate to call it a Floquet evolution, because you are not changing the parameters, you are only changing the number of iterations. So you choose some value of theta I, some set, and the same theta I you repeat 5 times, 10 times, etc. What you are varying is the number of iteration with the same values of theta, and see whether it gives you a reasonable good wave function.
You said with the same values of theta, right? In these Floquet operators, same values are applied periodically.
Yeah.
But then many times when the circuit is made, people like make all parameters independent.
You can make all of them different. Only thing is it makes your implementation more complicated without giving you any more advantage. That is the point. The point is not that I have a most general situation. The point is whether with a limited situation you can construct the same variety. And this gives an understanding that this much is sufficient. You can of course make more complicated things, but that does not gain you much in practice. How are the theta I determined? They are determined by minimizing the expectation value of h, as in the variational method. So you generate a possible candidates of psi theta I, calculate h for each one of them, and then you find an optimal value which gives you the lowest value of expectation for h. You can do it whichever way. You can make a grid of theta I. Yeah. Yeah, so generation of that grid of multiple values theta is kind of replaced by how many iteration of this psi theta you want to perform before you measure the expectation value of h. They are tuned. They are tuned. So you have to perform multiple rounds. That's till the whole thing converges. Choose some value of theta I, find the place where the edge gets minimized, restart with the new values of theta I, see whether you can improve it anything more or not, and repeat the exercise. It's a means kind of elaborate procedure. It does not finish in one round. But there is another connection to this. I will talk about it the next time. Is that can you see this disappearance of the fluctuations in the simulations of this Hamiltonian directly? And here you can actually make a comparison with this classical versus quantum behavior for different values of J. What happens in case of this changing this regular to chaotic behavior as a function of various parameters. And this was an exercise I gave to a master student a few years back, Ankit, and he did the numerical simulations and to find an answer. And it's a illustration of the fact that if you take J equal to half, there is no chaos at all. But even for J larger than half, you can actually see a difference between an evolution being reversible and irreversible. The instability of the chaotic behavior appears to the fact that the trajectories diverge and initial uncertainty gets magnified, and then it may not be able to track backwards to predict out where we came from. But the quantum dynamics brings in a certain reversibility in the sense that for every unitary operator you can define it inverse. The question is it possible to track back the evolution and ask whether the initial state is sensitive enough or not. And the problem which Ankit looked at was a simple machine learning problem. It was cut down to this description by the technique or rather the category of problem which is called binary classification. And the job was to just find out that initially the state is somewhere on the Bloch sphere, but it is a binary system. So it's, you can say that it's either in the northern hemisphere or the southern hemisphere. Run the Hamiltonian for a certain iterations and ask yourself, can you tell whether you came from the northern hemisphere or the southern hemisphere? This is what the whole industry of binary classification in machine learning keeps on asking. You want to divide the set of points into two classes, and can you do it efficiently? And here, all this quantum dynamics actually showed that yes, you can do it efficiently. And in that sense, because it was just a binary classification, there was perfect what you call invertibility of the algorithm, that no matter where the 2 points are, you can tell where they came from. So I will describe that next time. Another topic, machine learning, whatever it is.